faculty. The third is the main agenda, general lecture from Professor Karel. The fourth is questions and answers session. And the last is the closing. Those are today's agenda, which will be present soon. Ladies and gentlemen, let's open this event by saying Basmalah. Bismillahirrahmanirrahim. Excellencies, ladies and gentlemen, moving to the second agenda, which was an opening speech from the Faculty of Mathematics and Natural Science. Professor Widodo, PhD, Medical Science, time is yours.
Thank you, MC, for the times. Assalamualaikum warahmatullahi wabarakatuh. So let us express our gratitude to the merciful God who has granted us with the blessing and grace that we could gather here today to attend guest lecture on the variational approach finite element method. And first of all, I would like thanks to the Professor Karel from Department Mathematics and Graduate School of Science, University of Kyoto, Japan. And we also would like thanks to the Dr. Saiful Anam, Head of Mathematics Department, and also I think the committee and moderator today, Dr. Nur Sofiana, to arrange and all of these events. I think this very good events to open horizon for our student to understanding new finding and innovations from first hands, from Professor Karel's. I think he is very prominent scientist, and also this event is really important to strengthen our networks and international collaborations. Distinguished guests, ladies and gentlemen. So I would like also thanks to all of audience that who attends this seminar or lectures, and also I would like to give report to Professor Karel that now Brawijaya University already appointed by the Indonesia government to be autonomous university. So it is increase our maybe visibility and also for internationality. I think so we need your help, your collaborations, to improve our quality, and either in the teaching, learning, and also in the research. So therefore, I would like to propose collaboration with the Kyoto University, especially to conduct joint lecture, if possible, or at least you may allow our student to earn credit in your class or in University of the Kyoto. And I think this is very important for our students to expose international mindset, global mindsets. And this is very important for Indonesia, I think, for the young generations. Therefore, this is a real hope that you and also maybe your colleagues that will able to open more possibility for collaborations, in terms of research and also for the
sampai 10 nggak masuk rumah tak kunci.
And also finally of the fruitful, meaningful seminar or guest lecture today, I am as Dean Faculty Mathematics and Natural Sciences obviously open the guest lecture on the title Variational Approach Finite Element Method, and I wish you an enjoy talk, and thank you thank you one more for Professor Karel for your time. And I hope that guest lecture will beneficial and fruitful for all our students. Thank you so much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Professor Widodo. Can I talk? Is it okay?
Yes, sure.
Yeah. Thank you very much for the great introduction and for the invitation for collaboration in the future. Yeah, it would be great to do some collaboration and make your university more and more international. Yeah. So, and I also think that the 3-in-1 program is a great idea for the students, like to complement their curriculum with experience related to both industry, like application, and also scientific research, the theory. So I think it's a really valuable experience for the students, and I hope it will help them, and I am happy to be invited to contribute to this program. I am actually following up Mr. Robbie. In his first part, he talked about the industry part, application. So now is the theory part. And Sophie, can I start just the lecture already? Is it okay?
Maybe we will continue to the, I mean, it will back to MC first and then.
Oh, okay.
Yes.
Sorry.
Thank you very much, Professor Widodo, for officially opening the guest lecture today. Well, ladies and gentlemen, now we will start our session on the guest lecture by the variational approach to finite element method. Without any further ado, we would like to introduce Professor Karel as keynote speaker and Ms. Nur Sofiana, PhD, as a moderator. And Ms. Sophie, time is yours.
Thank you so much, Ms. Tika. So good afternoon, ladies and gentlemen. Welcome to our guest lecture of 3-in-1 program between Mathematics Department, Universitas Brawijaya, PT Rekayasa Pratama Consultant, and also Kyoto University. So here, let me introduce myself. My name is Nur Sofiana from Mathematics Department. Today I serve as a moderator in this case lecture. Just for the information, so this is the one of the program from Universitas Brawijaya, 3-in-1 program that collaborate between Universitas Brawijaya, industry, that is PT Rekayasa Pratama Consultant, and also overseas university. Here we our guest lecturer is Professor Karel Svadlenka from Kyoto University. So we hope that this program can enrich the introduction to finite element subject that one of subject in bachelor degree of mathematics department, so that our student yes can get more complete yes, complete about how about the finite element method, both in application and also in theory. Okay, and before Idul Fitri Day, we already have lecture from practitioner lecturer, that is from Mr. Robi, PT Rekayasa Pratama Consultant, and now we move to the guest lecture to study more deeply in the theory from Professor Karel as a visiting professor. Okay, so before we start the lecture, maybe I will, actually there are two sessions. That is the presentation from Karel, Professor Karel, and then the discussion session or Q&A session. But because of the limitation of time, we also welcome if during the lecture the participant has question, please write in the chat column of Zoom, or also or ask directly. We press the raise hand button first, and then yes, say the question. And yes, for the student, if you are maybe difficult to say your question with English, it is also okay. You say it in bahasa, and I will try to help you to translate so that Prof. Karel understand and can answer your question. Okay, before we begin the lecture, let me introduce Professor Karel Svadlenka with the curriculum vitae. Ms. Ika, could you please share screen?
Mr. Rizky, can you open my share screen?
Ya udah saya aja Mbak. Okay, I will share by myself. Okay. So our guest lecturer is Professor Karel Svadlenka from Kyoto University, and currently the affiliation is in Graduate School of Natural Science and Technology. I mean in Kyoto University, and this is the academic background. So Professor Karel take the master degree in Charles University in Prague, and he took 2 times doctoral degree in Charles University in Prague and also in Kanazawa University, Japan. And then this is some work experience, 2015 until now in Kyoto University, and before it 2009 until 2014 in Kanazawa University. And this is some scientific societies since 2006. This is the research topic, calculus of variation, partial differential equation, the numerical analysis and application to various fields such as material science, biology, or medicine. And he also be invited presentation, about 40 invited presentation and more 30 publication. And as we know from this short curriculum vitae that yes, Professor Karel have many contribution in numerical analysis, partial differential equation, and also finite element method field. Okay, let's begin the lecture. Welcome, Professor Karel Svadlenka. The time is yours.
Thank you very much. So let's start. So this lecture is designed mainly for the undergraduate students who take the finite element lecture given by Bu Sophie. So maybe for some participants it's too easy, or maybe it's too difficult. So sorry, but it's mainly
Mr. Karel, are you in mute?
Yes. What is the problem?
No, it's okay, Sensei. Please continue.
Okay. So if you find it difficult, please don't hesitate to ask questions during the lecture or after the lecture. In the discussion time is also okay. So I will share my slides if it's possible. Okay. Can you see the slides? Is it okay? Yes? Oh, okay. So, okay. If you want to contact me, please write to this email. Messages are welcome. And there is also, I made a simple website for this lecture where I put the lecture notes and also some sample codes. So if you are interested, please access here and download. It will be uploaded after each lecture. So there is nothing there yet, but today after the lecture, I will put some files there. Okay. So the lecture will be about how to solve differential equations using finite element method. And so this is the outline. So first I will introduce 5 typical problems that we will try to solve. Then I will focus on the simplest possible problem, one-dimensional Poisson equation, then go to a little higher level, higher dimensional Poisson equation. And in the final main part of the lecture, I will talk about how to solve nonlinear problems using finite element method. Okay, so this is the outline. So let's start with the sample problems. So the first, as I said, will be the 1D Poisson equation, which is very simple. So the equation looks like this. The minus second derivative of the unknown function u is equal to some given function f. And we have boundary conditions like this. So here f is a given L2 function. I will explain what it means in a minute. And UL and UR are real numbers. Okay, so this equation can, for example, describe approximately the shape of a hanging chain. Describe approximately the shape of hanging chain. So if I draw a picture, we have a chain like this. So it means the left end of the chain is at height UL and the right end of the chain has height UR. And the shape of the chain is the solution to this equation approximately. Okay, so here I set L2 function. So for those who don't know what is L2, I will give a brief overview. So I define it for general P. So I will define space LP on the interval AB. So this is the space of all measurable functions whose P's power integral is finite. So we can say these are all functions for which this integral is finite. And we equip this space with this norm. So the norm is just the P's power integrated, and when we integrate after that, we take the P's root, so the power 1 over P. So this is a norm, so it somehow measures the size of the functions. And when we take this space with this norm, we can show that it's a Banach space, which means complete normed space. Okay, this is theory, which is needed to give backgrounds to the finite element method. Okay, so how do such functions look like? So for example, the function x to power 1 over 4 is L2. y is in L201, let's say. Why? Because when we take the second power and integrate it from 0 to 1, we get what? We get 1 over x to 2. Sorry. Oh, I made a mistake. Sorry, it's x to minus 1 over 4. So if we take the second power, we get 1 over root of x, right? And this, we can integrate its root of x from 0 to 1, so it's 1. So this integral is finite, and the function belongs to L2. But when we draw the graph, the function looks like this, right? So it is unbounded. So the LP spaces contain unbounded functions. Another example is step function, for example. So take 0, 1. So some function like this. These functions are also in LP. So somehow in the classical formulation of the Poisson equation, the right-hand side, usually we say in mathematics it's a continuous function, so that the second derivative is a continuous function, and we can do the theory. But in practice, the right-hand side is not continuous often. So we need to deal with unbounded functions or functions which are discontinuous, like this step function. So as I wrote here, it is important to consider such wider class of functions than just continuous functions. Okay. So how to solve this equation? It's actually very easy to solve. We just integrate twice, right? Just integrate twice the function f. And when we integrate, we get two integration constants. So we can determine them from the boundary conditions. I forgot to write numbers, so let's put 1.2 are boundary conditions. So determine integration constants from boundary conditions. So actually, we do not need any finite element method to solve this problem. We just can solve it on paper. But to explain the theory or how the method works, it's a good example. Okay, so now the point is, what happens if we take f is not continuous function, but just some L2 function? So the question is how to define solution when f is not continuous, but only some L2 function, as we assume in the program. Okay, so this I will define in the next slide. Maybe, okay. Okay, so if f is continuous, we just integrate twice and everything is clear mathematically. But if it's L2, we need a more general notion of solution. So we define it like this. We call it weak solution, and some new space W12 appeared here. Sorry, I will explain it again in a minute. So we call a function belonging to this space weak solution. Weak solution to the problem 1112, provided it satisfies two conditions. The first condition is u prime, this is the derivative of u times phi prime integrated over 101 is equal to integral of 01 fx times phi x dx for all functions phi from 101. I will explain this space immediately. And plus boundary conditions. So we require the same boundary conditions. Okay. So this is number 1.1. So before I explain the idea of this definition, I will explain what is this space W12. This one. Okay. So the W1, again, I will explain for general P, what W1P on an interval AB is called the Subalife space. And it's quite simple to define. So just it's the space of functions which belong to LP, and their weak derivative belongs to LP. So both the function and its derivative belongs to LP. And again, we need some norm to measure size in this space, so we define the norm like this. The idea is just to add LP norms for the function itself and its derivative. So again, we can prove that this space with this norm is a Banach space, which is good for doing analysis. And also in the definition, I will go back to the previous slide. You see that there is some zero here. So the zero means, I explained it here. Yeah. These are functions which are zero at the endpoints AB. Okay. So, for example, this kind of function, if we take f like this, like piecewise linear function or piecewise affine function, this belongs to W1, let's say to any P01. So it is zero, as you see, it is zero at the endpoint. So this zero is okay. And it satisfies this condition. It may be hard to see immediately, but you can believe me. So the point is that the derivative is discontinuous, right? If you calculate the derivative of this function, you get something like some discontinuous function like this. So the function, the Subalife space somehow has functions which can be differentiated, but the derivative is not so nice. Okay. Is it difficult? Do you have any questions up to now? No question. Okay, so I will explain one more thing. There is, I said weak derivative here. I said weak derivative. What does it mean, weak derivative? You know the usual derivative, but we are talking about a little different derivative, which is called weak derivative. And this is defined like this. So if we have a function f, so then its weak derivative, let's denote it by g. So this g is the weak derivative of f, is a function which satisfies this condition. what is the idea is here that if you look at the left-hand side, so this, if we do by parts integration, then we put the derivative on the function f, and there will be some boundary term, let's say f times f from a to b, right? So basically we get, and this is equal to 0 because we are assuming that phi is from this space. So C0 means that it's 0 near the boundary. So C0 infinity is the space of infinitely differentiable functions which are 0 near the endpoints AB. So this term, because we take only the values of phi at A and B, these terms will be 0. So the left-hand side, so actually we get this equality, right? But this means that if f has the usual derivative, so we can do this by parts, then it means that actually f prime is equal to g. So the weak derivative is the usual derivative that we know. So if f is differentiable, then the weak derivative coincides with the usual derivative that we know. But if it's not differentiable, it still can have weak derivative if it satisfies this condition. So this is the idea. Okay. So for example, the weak, if we take the function absolute value, then the weak derivative is I will draw the graph. -1 here, and for positive x, it's +1. We can, I will not do it here, but we can check that this function satisfies this condition here. So it's weak derivative. So absolute value, we know that is not differentiable at 0, right? But it still has weak derivative. And the point here is that we don't need to define the function at 0, the weak derivative. It can have any value at 0. And the reason is because we are integrating everything. So if we integrate a function, the value of the function at one point does not matter for the integral, right? So if we define the weak derivative at 0 as 0 or at 1, -1, it does not matter. It's the same function. Okay. Maybe it's very rough explanation. Okay, but I think it's enough if you remember that the Subalife space is the space of functions which can be differentiated in some sense, and the derivative and the function belong to LP. So this is the meaning of this function space here. Okay. So what should we do next? Okay. Okay. So how did we obtain this weak formulation, weak solution, the definition of weak solution? So 1.3 was obtained by multiplying the Poisson equation, which was 1.1, by the function phi, integrating over the interval 0, 1, and doing by parts. So I will do it. So we had this equation, right? This is the Poisson equation. I multiplied by phi. Then I integrate it from 0 to 1. And finally did by parts in the left-hand side. So I got this. And this is exactly the equation 1.3. Okay, so what is the point here? What is the point of this definition? So there are maybe three things which are good about it. So one is everything is integrated. So we don't need the functions to be defined everywhere. So u and the derivative of the solution can be only L2 functions. They don't have to be defined everywhere. And maybe the best thing about it is only first order derivative appears in the equation. Which is different from the original equation, right? For the original equation here, there were two second order derivatives. But in this equation, there is only one first order. So somehow chance for solution to exist increases. Because we need only one derivative to exist. So it can happen that the original formulation does not have solution, but this weak solution exists. Okay, and the last point is, which is also important for us, is it is the starting point to derive the finite element method. So is everything okay? This is about the 1D Poisson equation. Next, we will go to a little more difficult problem. So if there is any question at this point. No?
Is there any question from the participant?
Okay. Yeah.
Maybe.
Okay,
Yes,
let's
still-
go.
Yes.
Yeah, let's go to the next program, which is a little higher level, so higher dimensional Poisson equation. And the problem looks like this. So the Laplacian of u is equal to some given function f in some domain omega, and the boundary condition is given by some function g. So on the boundary of omega, so this means boundary of omega. Okay. So this is the problem. And so omega, let's say it's a d-dimensional domain. And we are solving the Poisson equation in this domain. And the del omega is boundary of omega, and we assume that it's sufficiently smooth. I will not go into details. We need for the theories that it's not too rough, like some fractal will not work for us. So it must be like rectangle is okay, circle is okay, and it has to be smooth enough. Okay, and f again is a function from L2. Now it's not on the interval, but it's on the domain omega, but it's the same. And g is a function defined on the boundary of omega. But let's make things simple, and let's take just g is equal to 0, so that it does not get complicated too much. We can easily change it if we want. Okay. And maybe some of the audience don't know what is this triangle, so I will define this is the Laplace operator. So it means we are adding all second order derivatives, like with respect to the same variable. So for example, into D, the Laplacian is just del x second order derivative and with respect to y. So this is the Laplace operator. And now before, okay, let's say what this equation can describe. So you can find it almost anywhere in any field of science. So I will write this ubiquitous in science. So for example, it can describe the potential fields. Like electric field, for example. So you know if we have plus minus, then there is some like the field lines like this, and if the field has a potential, then it satisfies this Poisson equation, where the right-hand side is the charge or is related to the charge. So F, the right-hand side, F is related to the charge which generates the field. So it's really a very common equation. And okay, I will briefly explain about L2 omega, because before we explained it for an interval, but it's actually the definition is completely the same. So LP omega is the space of functions whose piece power has finite integral over omega. And W1P, again, Subalife space, is the same, is the space of functions which belong to LP omega, and this derivative also belongs to LP omega. But now, as you know, the derivative, there is not just one derivative, but there are d derivatives, right, in d dimensions. So the gradient vector, which has all the derivatives in it, is a d-dimensional vector. So there are d derivatives. So we need to define the norm a little different way, like this. So we take the norm of the gradient, which actually means that we are adding all the piece powers of all the derivatives like this. So yeah, it's some form of the differences in higher dimensions. Okay. What is a big difference? I will underline here. So is that W1P functions need not be continuous in higher dimensions. So if in one dimension all W1P's functions are continuous, but in higher dimensions they do not need to be continuous. So then it becomes a little difficult how to define zero boundary condition because the function may not be continuous, but I will skip the details. If you are interested, you can check some textbooks on Subalife spaces. Yeah, there are many. I put in the lecture notes some references. Okay. So okay, let's okay. So this problem, the Poisson equation is not so easy to solve now, especially when omega has some complicated shape. So if omega has a complicated shape, it is hard to solve analytically and has to be solved numerically. And now at this point, the finite element method becomes useful. But we will talk about it later. Okay, so before that, let's practice some theory and write the definition of weak solution. Of the higher dimensional Poisson equation. So I will write shortly. So now the definition becomes like this. The form is almost the same as for 1D, but like somehow some symbols are a little different. And what is different is this gradient, right? Instead of derivative, we have gradient here. And so this is gradient is a vector. So this dot here is the dot product of two vectors. Now, you know the Euclidean inner product or dot product. So we are taking the dot product of these two vectors. And okay, again, I will skip it. You can try to do it. The weak formulation is obtained in the same way as in 1D. So it means I multiplied the test function to this equation, integrated over omega, and did by parts. So this part is a little difficult. How do we get this omega? Yeah, how do we get this? This may be a little difficult. I will leave it up to you. And let's go to the next problem. Again, level up. Okay, so the next problem is P Laplace equation. And the form is like this. It's actually almost the same as before, only this P is new. And what does it mean? So the Laplace operator changed to this P Laplacian. This is P Laplacian or P Laplace operator, and it is defined like this This is divergence operator. Like this. Okay, so I will explain a little more. So divergence of a vector, probably you know, but I will explain. So it's the sum of all partial derivatives. Like this. Okay, and so this is the divergence, and this is the gradient of u, and we are taking its Euclidean norm. So it means we are taking du dx1 squared plus du dx2 squared plus and up to dxd del u del xd squared and take the root. Okay, so quite complicated, right? So to see what is the P Laplace equation about, let's investigate special cases. So one special case is when P is 2. What happens when P is 2 and the dimension is arbitrary? So what happens? So we are computing the 2 Laplacian. So it becomes divergence of, and now P is 2, so P minus 2 becomes 0. So this norm of gradient vanishes, it's not there. We just get this. And this is actually equal to Laplace of u. You can try to check it. So for P equals 2, it is the usual Laplacian. So we can say that the P Laplacian is a generalization of the Laplacian. Let's try one more case. When P is 4 and D is 1, so one dimension. So then if it's one dimension, then the gradient is just the usual derivative. There is only one variable, right? So the gradient is just usual derivative. And so we get that the 4 Laplacian of u is, okay, so and maybe I should write divergence of some vector is just again the derivative of the vector. So we get now P is 4, so we have derivative of u squared times derivative of u, and the whole is divergence, so again derivative. So this is u derivative cube derivative, so it's 3 u derivative squared u second derivative. I hope you can follow. So we see somehow, so it is a nonlinear operator. Right, because we have second order derivative multiplied by the square of first order derivative, so it's a nonlinear operator. And we are, so the P Laplace equation, sorry, the P Laplace equation here, equation 1.10 and 11, is a nonlinear partial differential equation. So it's very quite high level to solve it. Okay, I maybe should say equation has many applications also. For example, in rheology, radiation of heat, yeah, plastic molding, and so on. So it's also often used. Okay, so how to define its solution? I did not say, okay, that f is, again, we take L2 function. So we need weak weak version of solution, and it is the same idea as up to now. So when we do the same procedure, we multiply our equation by a test function phi, integrate and do by parts. What do we get is this. And this is for all, let's say phi in C0 infinity omega. Up to now we had W1 something. Don't worry about this, it's not so important. It's a detail, so the test function we take now from C0 infinity to avoid some problems. Just okay, so this is the weak formulation, and so here we used the divergence theorem to derive it. So the divergence theorem, or its version, okay, sorry. So we use this kind of green formula, which follows from the divergence theorem. So it's basically some part by parts integration in higher dimensions. Right, so we could, we have divergence of V, and we transferred this derivative to the test function phi. We have gradient of phi, and we use this on the vector V is equal to this gradient of u to p minus 2 gradient of u. So if you think about it, this integral is the same as this one, right? So hopefully you can see how we got it. Just this integral is 0 equals 0 because phi is 0 on the boundary of our domain omega. I think it's getting complicated. So now, is there any question now? No.
Yes, for the participant, is there any question until this stage? Maybe.
Sophie, you don't have any question? No. Okay. Okay. If no question, no?
No, so maybe you can continue first.
Yeah, let's continue. Let's continue to higher level. Maybe it's not so high level. To the fourth example, which is equations of linear elasticity. So to describe the deformation of some elastic body, we use the following equations. and I will write them only for the special case when the elastic body is isotropic. So it has everywhere has the same properties, material properties. Okay, so the equation, the governing equation looks like this. Plus lambda divergence u times unit plus f in some domain omega, and we have boundary conditions. I will explain. This is one boundary condition, and to write the second one, let's denote this whole thing denote by sigma of u, so that we don't have to write so long equation, and sigma of u times autonormal n is equal to some given function gn. Okay, so what is going on here? So we have, let's say, some body which is not deformed. So this is omega, the original body, let's say in 3D space, and we exert some force on it, so it will deform into some other shape. And this will not fit here. Omega. And the deformation is described so by how points from the original body move or where they are transferred during the deformation. So for example, this capital X, let's say it will move to this point small x. So the deformation is now described by the displacement u. So now what I wrote here, so the new point small x is the original point x plus some displacement. And the displacement is given by the function u, and it is a vector. So basically, we can draw the vector u here in this picture, like it's very long, sorry. This is the vector u, right? From here to here. Right, so this u has this meaning. So it's a vector valued function, and it describes the deformation. Okay, and the equations look like this. Maybe I should write u. So it has sense to consider elastic deformation in our 3D world, 3D space. So u will be a function from R3 to R3. So the meaning is the displacement between points in the original domain omega and the corresponding points in the current domain or the deformed domain omega t. And what we have, mu and lambda are material constants. So they describe how the body reacts to outer forces when we stretch it or squish it or compress it. So if the material is isotropic, it can be described by just two constants. And what more? We have this omega d and omega n. So I will picture. This is omega. So its boundary is del omega, and it is split into two parts. One is del omega d, and the other is del omega n. And on each part of the each part of the boundary we prescribe different conditions. So on del omega d, we prescribe fixed, so the shape is fixed to a given position, and on del omega n, given traction, some force is given on the boundary. So we can have such general boundary condition. Okay. So let's look what is going on in the equation a little more. I said u is a vector valued function, right? So what is the gradient of u? So since u is a vector, like it has three components, u1, u2, u3. So the gradient is a matrix now. It becomes a matrix. In the first row, we have partial derivatives of u1 with respect to, I will write, so I will write dx, del x, just del y, del z. In the second row, we have del 2, del x, del 2, del u2, del y, del u2, del z, and the third row has partials of u3. So it's 3 by 3 matrix. And this T means transpose. Of the matrix. Okay. What time is it? It's already like. Okay, I will very briefly describe. I have already prepared some notes how this equation is derived. Maybe it will be very fast, but I think I should explain. So basically, the equation 14, the main equation, is a balance of forces. So the right-hand side F is some force which is exerted on the body and causes the deformation, and the left-hand side is the force within the body which like arises due to the stresses through the deformation. So this I wrote here. And the internal forces are fully given by the so-called stress tensor or Cauchy stress tensor. So if we have a body like this and we cut it by some plane with normal n, then at some point x, let's say, so this stress tensor sigma times n gives us the force on the plane at the point x. Somehow, so this stress tensor describes the internal forces within the body. So to derive the main equation, we just write the balance of forces for any subdomain of our body. So if we have the whole body like omega like this, we take some small subdomain V and write the balance of forces for this V. So it is written here. So the forces that are exerted on the body or on this subdomain V must be balanced by the internal stresses, the total of the internal stresses which act on the boundary of V. And when we apply divergence theorem, we get this equation. Okay, I will go fast. And so now it remains to look at how are the internal stresses related to the displacement u. So if there is a deformation, spatial deformation of the body, how can we find the forces or the stresses inside the body due to this deformation? So for this, we need to measure, we need some measure of strain. So how big is the deformation? How big is the spatial deformation? And the idea is to look at so if the original body, we take 2 points where x2 is x1 plus v, some vector v. So we look at this distance, and after deformation, they change to x1, small x2, like this. So before deformation, the distance of the 2 points is just this v. Okay, I will take the square distance. So we can write it also as v transpose unit matrix v. And after deformation, we have x1 minus x2. And x1 is given by x1 plus u of x1, the displacement, right? Minus, and x2 is x1 plus v plus u of x1 plus v. Okay, it's complicated. And if we calculate this, we get, this is approximately when we do Taylor expansion, we get this. Okay. So it is natural to measure the strain or how big is the deformation just by taking the difference of this unit matrix and this matrix. And this is exactly here. So this is here and this is here. So this matrix E of U, this one, is a measure for strain or for how big is the deformation. And in the linear theory, we just assume that the strains, the deformation is small or the displacement gradient is small, so we just omit this term. So what we end up with is, let's say, epsilon of u, which is 1/2 of this. Maybe you remember this kind of thing appeared in the equation. Okay. So now we have a measure for strain, and then we need to write some relation between strain and stress. And we use the generalized Hooke's law, so you know from spring that the spring acting on a force, the force acting on a spring is proportional to the extension of the spring. So it's exactly the same thing, just generalized for like higher dimensions, for 3 dimensions. So it's a linear relation between the strain depends, stress depends linearly on the strain. And because we are in 3D, there are generally 81 components in the linear relation. So many, this is like 3 times 3 times 3 times 3 because it's a 4-order tensor. But there are some symmetric considerations, and if the material is isotropic, these can be reduced just to 2. And these are those mu and lambda that I showed in the equations. So, yeah. And when we rewrite this equation, we get this kind of equation for the relation between stress and strain. And when we have the linear theory, this still simplifies to this form. Okay. So this is the strain. And you see that if I go back, that exactly this formula is here. So it was very fast, sorry, but the derivation, the outline is like this. We can derive the equations like this. And I should write the last equation. Of nonlinear elasticity. Okay. I think I should go towards the end already, so how to do it? Okay. If the deformation is just rotation, there should be no strain, right? If we just take the body and rotate it, then there is no strain and no force appears due to the rotation. But in linear elasticity, there is actually strain. So it's not really good model because this u epsilon of u, which was this, is not zero for rotations. In fact, the previous u, the original, the precise one, which was this. So I forgot there's 1/2 everywhere. So this one is 0 for rotations. So the precise form of the strain is 0, but when we linearize it, it becomes not really physical. So the physical meaning is a little weak for the linear elasticity. So if there are no big rotations, it's a good approximation. But if there are big rotations or big distortions, then the linear elasticity is already not a good model. So I will write it for big distortions. Linear elasticity is not a suitable model. Yes. Should I already?
There is participant who raised hand. Is it
okay?
Okay, please, Ms. Umuhabita.
Okay, thank you very much, Professor Karel. I would like to ask a question. In the previous section about equation of linear elasticity, in this equation, I mean, the equation of linear elasticity describes the deformation of an isotropic elastic body. So, my question is about the material. So, in this case, we should consider about the material. If, for example, we should consider about the fluid or because there is the deformation here. And for the neck, this is should be solved by finite element. As I know, finite element is the method for solving, I mean, for solid case. So what happened about this? It is for fluid or also for solid? Yes.
These equations are for solid. Actually, yeah, this is a good question, because for fluid, actually, we have a similar equation, but like fluid is different. Yeah, so, okay. For fluid, actually, the particles can go like very, very complicated. The displacement of the particles can be very complicated. They can go in circles and so on, but solid is not so. The deformations are, the matter cannot interpret and interpretate. So the deformation can be described by the displacement. But for fluid, it's not. It's better to use the Lagrangian description, so the equations becomes different, and also physically the laws that govern the fluid are different, a little different from solid. So the equation becomes a little different. But the idea and the form of the equations are very similar. So we can solve both of them using finite element methods, of course. Yeah. I don't know if that's what you asked.
So I mean, for solid, can solid change like this? I mean, very deform like this, or just change the what is the trend?
Yes, right.
Yes, I mean not too much change like this. For solid. Yes.
Yes.
Is it correct?
Yes, yes. It's the idea is like that. That fluid can have very the particles. They can go like this, right? They can go in the fluid, like the particle can move like this. So, but in the solid body, like it's very restricted. It cannot go like this, right? It would, then the matter will go through itself somehow, and it's not possible. Yeah, so we use a different mathematical description for fluid than for solid.
Okay. So we cannot use the case of fluid to in this equation.
Basically, no. Unless the fluid is very, very nice fluid, it does not float too much. Yeah,
Yes. Okay, thank you very much.
Yeah, thank you for the question.
Yes.
Okay. I wanted to say more, but I think time is coming. So let's leave this next topic for next lecture. I will just give up writing the equations because they are very complicated and the form would not tell anything to us. So we give up writing the explicit form, but later we will look at them on the level of energy, which is much easier to somehow understand and write. The form of energy will be much easier than the equations. So we will not write them here, but later we will go back to it and write the model exactly. So this is the variational approach. Yeah, it's actually why it's a nice question, because why I chose elastic body, because for fluids, it's possible to write some variational approach, but it's not so easy. It's much more, yeah, the solid body is much better for variational approaches. Okay, so thank you very much for your attention. And if there are any more questions, then I will stop the lecture here, and please ask any questions or give comments what could be improved.
Okay, so is this correct that this is the we will move to discussion session, Sensei?
Yeah.
Okay.
Yeah.
So yes, thank you very much for the very interesting talk. Now in short, very short remaining time, maybe is there any question from the participant? You can asking directly. Okay, maybe yes, while. Oh, Adli. Yes, please Adli. Speak directly.
Okay, thanks for the opportunity to let me ask questions. So, is it just so happens that a lot of physics applications benefits from finite element method, or is it that finite element method are first made specifically for physics application? Because from my research, all I can see about, or all I can find about finite element methods is mainly focused on physics application, and I haven't found any other case. I think that's for my question.
I see. Yeah, thank you. So yes, basically, yeah, I think you are right, because you are talking about applications and kind of theory or like scientific research, right? So in applications, usually we have everything is much more complicated than in science. In science, we take our domain will be just a rectangle, and let's solve our problem on rectangle. But in application, the domain is very complicated. Let's say it's the bridge or very complicated structure. So it's a very different problem, right? If the domain is very simple, we don't need to use finite element method. We can solve the problem by other simpler methods. But if the domain is very complicated, we need finite element method. We need to discretize this, just triangulate, right, and so on, so that we can solve it on this complex domain. So I think this is the reason why you use a finite element method for application problems or physics problems mainly. Yeah. Is it what you wanted to ask?
Adli? Adli? Is it enough?
I think it's enough for now. Thanks for the answers, Mr. Karel.
Thank you.
Okay, thank you. Adli is one of the participant in finite element method subject, Sensei.
I see. Yeah.
Yes. Okay, I think still is very, very short remaining time. Is there any question? Okay. I don't think there is anybody that raised hand. Okay, so while waiting the other question, maybe could you please how to say, restate in the clearly statement. I mean, related with the application that Mr. Robi have explained in the previous lecture. So in that case, yes, what kind of the equation in your explanation is there the appropriate equation, or maybe we need some more complex equation?
Yeah, I'm not sure. I'm not sure what the equation, because in his slides there is no equation, so I'm not sure. But I think that they use this kind of equation. They use linear elasticity equation to solve the deformation of the bridge, for example, or so. Yeah. I don't think they use nonlinear because it's really difficult to solve, and the deformation there is quite small. I would say. I'm not so sure. It is in Bahasa, so I'm not sure. But I think the parts of the bridge deform, but not too much. So linear elasticity is okay to use as a model. So I think they solve this set of equation on this slide. Yeah.
Okay, Sensei. Yes, thank you very much. I hope the student can catch up and connecting between the previous lecture that is in application and also in yes, this theory. Okay, I think the time is yes,
Yeah.
yes, the time is it is maybe because the time is in, this is the end of the guest lecture time. So once again, I say thank you very much to Professor Karel for very, very interesting the talk. And yes, I hope the participant can understand, because the understanding in material today, maybe it's really helpful to continue the next meeting, right? Yes.
I will explain.
Yes, Sensei.
Yeah, I will explain more about the equations in the next lecture.
Yes.
How to solve them. Yeah.
Yes. Okay, thank you very much. And now, yes, I will give back to the MC, Jessica, please. Thank you.
Okay, thank you, Miss Sophie. It's a very interesting material and we all really enjoy it. For the documentation, we are going to have a photo session, all right, because we have some screen page in this conference, so it will take a few time to take a picture, and our committee will take your picture in every screen, so please open your camera. Can you stop share screen, Mr.? Okay, thank you. Okay, Mr. Rizky, maybe you can help me to take a picture in every screen. Please, our participant, to open your camera. Okay, thank you. Finally, we get to the last session in this event. Let's close this event by saying Hamdalah. Alhamdulillahirabbil alamin. And don't forget to attend to the next session on May 24th and 25th. And as the master ceremony, thanks to Professor Karel, Professor Widodo, Miss Sophie, all lecturer and all students from mathematics department. And what we had gathered will be useful for us. And for the deep of my heart, I do and apologize for my mistakes while in presenting this event. Thank you very much for your attention and nice to see you all. Wassalamualaikum warahmatullahi wabarakatuh. See you next session and bye-bye.
Bye.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you very much, Mr. Karel.
Sensei.